Welcome to Chapter 11, our final chapter. Only three sections in this, and this chapter is going to go really fast. Some of it is because there's a great deal of review of pre-calculus concepts. Some of it is because all three sections are going to be done pretty similarly to this first one. And finally, I want to make sure we get in our 2 weeks of review before the AP test. So section one is on parametrics, and we've done a little bit of this already way back in chapter 3 when we found derivative of y with respect to x when we have parametric functions. And in section 2, we're going to deal with vectors. Section 3, when we deal with polar, they're going to be done very similarly to this. Uh, with vectors, it's actually just parametrics just written in a vector form. With polar, we think of them as being x and y being defined with respect to theta rather than being with respect to t. But remember that the idea of parametric functions is that x and y are both dependent variables, and our independent variable is t. Um, and so, for example, I could have x equals cosine of t, y equals sine of t. And the biggest key here is just remembering that t doesn't show up on our graph. Our graph is still x and y axes. T, I think of as t is the variable that shows us where the points are as we draw them. So it's kind of the order we draw this in. So kind of, for example, here, if I were graphing this first one, cosine t, sine of t, and t is going from 0 to 2 pi, well, if t is 0, my x would be 1, and my y would be 0. At pi over 2, x would be 0, y would be 1. At pi, x would be -1, y would be 0. At 3 pi over 2, x would be 0, y would be -1. And I'd have to connect these in that order, and so I would actually get a circle here. And 2 pi, even though it's not included, would take me back to 1, 0 for the coordinates. Similarly, if I were given something like 3 cosine of t, 2 sine of t, when t is going from 0 to 4 pi, starting out when t is 0, and I could just keep picking values that are easy to find, so like pi over 2 would put me here, 3 pi would put me here, 3 pi over 2, and then if I get to 2 pi, I'm back to here, and then I actually just repeat this, and I get an ellipse. Now, we are able to graph these on our calculator, if you remember. So to do that, remember, we had to go into our mode and switch the mode to parametric right here. And then when we hit the y equals button, we can enter them in pairs. So for example, here, the square root of t for the x and t minus 2 for the y's. And the nice thing is when we graph this, we can actually see the order it's being done in. And let me fix my window for my x's. So my x's, because we're looking for t from 0 to 4, so my x's should go from 0 to 2. Well, so t goes from 0 to 4, and then zoom fit. So it'll actually change my x's and y's for me. And I can actually see it graphs it in that order. And if I need it to slow down, I can just hit trace, and it'll trace it in the order that it's done. So I can see then that this graph, t would be 0, takes me off uh, this way. And that's a really nice part of our calculator. The other part that we had already discussed is finding slope of a parametric, where dy dx is dy dt over dx dt. And we're still going to be doing that because remember, the slope of our curve, since our graph doesn't include t as an axis, when we're talking about the slope of the curve, it's still dy dx, but our y's and x's are defined in terms of t. So we're just taking advantage of Leibniz notation there to cancel out the dt's. Second derivatives for parametrics are done a little bit differently, in that we would take our dy dx and find its derivative with respect to t, and then divide that by dx dt again. And that's just to get my dt's to cancel and get my dx squared on the bottom. Next video, we'll go through an example of that.